Okay, in general, this is how you compute the distributions of functions of random variables. If you change the distribution of x, if you change the function that defines y, of course, there will be different approaches. Usually, there might be more than one way to compute the distributions. And in fact, even with this question, I'm going to show you a second way where we just um, condition the CDF of y um, on the range of x. Okay, so we are going to make use of the law of total probability, and we will just condition this event which defines the CDF of y on the value of x, but not the exact value of x, but just on the interval, because you see x takes values from -1 up to 2. So I'm just going to consider three distinct cases where x is between -1 and 0, and x is between 0 and 1, and x is between 1 and 2. You see, this is the PDF, and the PDF value is 1 over 3 throughout. But when you condition x on each of these regions, you see, since the PDF is flat, the probability that x falls within each of these three regions is equal, because this is a uniform distribution. So each of them has 1 over 3 probability. And when you actually compute the conditional distribution of x, it will be for from -1 to 0, this is 1. And from 0 to 1, again, this will be 1, because it will be normalized by 1 over 3. And from 1 to 2, this will again be 1. These are the conditional distributions of x given you are in this region. Okay, so returning to the CDF expression, y less than or equal to y, this is obviously x squared less than or equal to y, but you see, I'm conditioning this on first x being in the region from -1 to 0, and then to 0 to 1, and finally 1 to 2. Okay, so this expression is nothing but an application of the law of total probability, since these three events, -1, 0, 0, 1, and 1, 2. Okay, well, we do have the intersections here. Maybe you can eliminate this 0 here and this 1 here if you like, or maybe keep this 0 here, eliminate the 0 here, keep this 1 here, eliminate the 1 here. Doesn't really matter, because the distribution of x is continuous. Okay, but of course, in general, you have to be careful about those bounds. But for this specific example, it doesn't really make a difference. So I have just conditioned the CDF of y on these three regions. You see, this give me the sample space of x, and if I'm careful with these inequalities, these three define a partition. Okay, so one of these, well, each of these probabilities of x being in each of these regions, as I said, are 1 over 3, since the distribution of x is uniform. Okay, so what remains is finding out these conditional distributions. And when well, we will have to look at the probability here with respect to y, the parameter y, for different regions. Obviously, when y is negative, the probability is 0. Okay, and when y is above 4, since x is confined from -1 up to 2, square of x cannot be larger than 4. So when y is larger than 4, this probability will be 1. It will be a certain event. And in between, I'm going to look at the region where y is between 0 and 1, and y is between 1 and 4 separately. So when y is between 0 and 1, let's look at this. The probability that x squared is less than or equal to y, given x is between -1 and 0. Okay, so that I can find with integrating this conditional PDF, which takes the value of 1 here, this, okay, from minus square root y up to 0. Minus square root y somewhere here. Okay, so this region will be the event, x squared less than or equal to y. Okay, and this 1 over 3 is this. It's not the PDF of x. The PDF is here, the conditional PDF. Okay, coming from this. And the second term here, again, this 1 over 3 appears here. Okay, and this probability, how can I find this? X squared less than or equal to y, given x is between 0 and 1. So I'm here. Okay, so my event is here from 0 up to square root y. So that is the limits of this integral. And what is integrated is 1, which is the conditional PDF in this region. And plus the third term here, again, this 1 over 3 appears here. But you see, x squared less than or equal to y. But remember, y is between 0 and 1. And therefore, this probability here is 0. Because when x is between 1 and 2, the square of x should be greater than 1. But y is not greater than 1. So no outcome will satisfy this. Therefore, the probability for this will be 0. And if you compute this, you get the exact same result. Let me a little bit clear this out. Okay, since the integration is trivial, we can directly write this as this one here. You see, this here is just 0 minus square root y, but divided by 3. And this here is square root y minus 0 divided by 3. So you get 2 square root y divided by 3 as earlier. Okay, and for this region, y between 1 and 4, again, all these have 1 over 3 probabilities, which appear here. Okay, but then when you look at these conditional probabilities, remember y is above 1. It's below 4, but it's above 1. So when x is between -1 and 0, x squared less than or equal to y is a certain event, because x is less than well, it's greater than or equal to -1 and less than or equal to 0. So it's between -1 and 0. So its square is between 0 and 1. But y is between 1 and 4. So it's definitely greater than or equal to x squared. So the probability here is 1, which is seen here. Very similarly, when x is between 0 and 1, again, this is a certain event. So probability 1 here. What about this one? X squared less than or equal to y. When x is between 1 and 2, I will just integrate this PDF here from 1 up to square root y. Because y is between 1 and 4, its root will be between 1 and 2. And I'm integrating the conditional PDF, which is 1, okay, from 1 up to square root y. From 1 up to square root y. Okay, again, this gives me 1 over 3. This is 1 over 3. And this is square root y minus 1 divided by 3. So that is 2 plus square root y minus 1 over 3, which gives me square root y plus 1 over 3, which is exactly the same expression as we have computed before for the CDF.